Am I audible?
Yes, sir.
Okay. So what I'm thinking is I'll be starting with the content of uh, week 11. Okay. Last time we revised first 4 weeks. So this time I'll uh, finish that week 11 content that was covered by the instructor. We'll quickly have a recap on that and do some basic problems on that. And towards the end of the session, if time permits, we'll try to revise the next 4 weeks. Okay, from week 5 to week 8, we'll try to revise. Is that fine?
Okay, sir.
Or
Okay.
okay,
Yes, sir. Yes, sir.
I'll share in a moment. And by the way, how's the exam preparation going on?
Sir, just going on, sir. We can revise, sir, first two lectures.
Okay.
Not try to solve, sir, the question which we are say that these are some harder problem. We just focus on the problem which you discuss in the classes.
Okay, I
And
mean,
the
you can do one thing. You can try to revise whatever notes you have taken during the instructor lectures that you saw, and you can practice the problems that I and the other two TAs have shown. I guess those problems and your assignment problems are sufficient. Don't miss out the assignment problems. Make sure you do them. Okay.
sir, so your
Yeah.
suggestion is that first of all we can solve the assignment problem,
Yeah.
and then we can solve the problem which you discuss beyond assignment.
Yeah, that would be the best approach. And by the way, you can leave those supplementary problems that I had. Remember, I had some
Yes,
supplementary problems. I
I
thought
I, I
someone
try.
would make, yeah, I thought someone would discuss that over mail, but since nobody discussed them, and also for the scope of this course that are way harder, so don't worry about them. You can just skip them for now. Do the problems that we solved in the class or next. Okay.
Actually, sir, I try for the core problem you are discuss with the first class week
Hmm.
one.
Yeah.
Week one, sir. But I find that they have some complex integration is there. So
Okay.
as the time is limited, sir. Actually, basically, I am working and maximum of
Yeah, yeah,
working
yeah. You
with
we discussed that
with
last time. Yes, I can understand.
yes, sir. With I have to manage the family, sir.
Yes,
So
yes, yes.
I just first of all I just solved the, sir, problem which you are discussed. I can move to the past 2 weeks have been completed. Then I
Mhm.
can do the assignments. The rest of things, sir, I don't know whatever happened, sir.
That will be
Because, sir,
fine. Just try to put in best possible effort. Everything will be fine. Just
thank you,
switching
sir.
on my
Thank you.
iPad. Just switching on my iPad. I'll share. Just switching. One second. I'll need 2, 3 more minutes. Okay, so that the iPad is switching on now. Once it switches on, then I'll be able to share. This would be our week 12 session, but the content that it would have would be from week 11, right? Since we missed week 11 last time in the pursuit of revising first 4 weeks. Okay, my iPad is on. Let me just join my iPad first. It's 2025, week 11. All right. So, just a second. Okay. Sorry for the delay. For those of you who are watching it in recorded form, you may, I guess it's already too late to say that, but yeah, first 10 minutes. Okay, now let's start with a week 12 session. Okay, so welcome everyone to the course NPTEL 539, titled Fundamentals of Semiconductor Devices, taught by instructor Professor Vijay. I'll be the TA for this session, and the schedule for my sessions was every Sunday 3 p.m. to 5 p.m. Okay, I have a little announcement for you all. Maybe NPTEL team would have already posted it on the portal, but tomorrow 3 p.m. we'll have extra session. Okay, and that would be the last session of this series from my side. Let's go to the guidelines again.
Sir,
Yeah.
in that session, you can discuss uh, entire 12 weeks, no? Just revise because I have also attended one session, different subjects.
Okay.
So
Actually, we have this week 12 session, right? We
okay,
did not
okay.
finish that. I mean, if no one, okay, let's do one thing. If all of you want me to revise, then don't do anything. If anyone is against this idea, he can either let me know in this session or post a comment on the YouTube. I guess if I get a comment on YouTube that someone wants the content corresponding to week 12, then I'll accordingly prepare. But I need the comment by today evening. Okay. Let's say today 9 p.m. If by today 9 p.m. I get such comment, then I won't be revising. Else I'll revise. Okay. What do you want me to revise?
Sir, actually, I don't know what about others. It's my personal opinion that you can revise from 4 to 8 weeks. Sir.
You mean 5 to 8, right? 1 to 4 we already touched.
1 to 4, yes, 1 to 4, yes.
Yeah, 5 to 8.
Five
Sure,
to
I'll.
eight, sir. And
Okay.
and sir, if possible, sir, we have revised 1 to 4 tomorrow. And if there is any problem is there, you can also discuss this.
You want me to revise 1 to 4 again?
No, sir. No, sir.
Then
I just say that we ourselves prepare for 1 to 4, whatever you can discuss in last
okay,
session.
fine. Whatever you have doubts, you can come up with them.
Yes.
Write them in
Now,
your notebook. You can either mail me beforehand, or you can just ask me in the session directly. For
yes, sir. Yes.
week 1 to week 4, I mean, I'll find that.
Actually, sir, I think if I do
Mhm.
1 to 8 weeks complete revise from anyone, sir, those who are taking your live classes, I think
Mhm.
this will be maximum for the exam, because 9, 10, 11, 12 weeks are some applications are there. I think so.
Yeah, I mean, I don't have any issues.
Basic,
Just that I need to take into confidence everyone. That is my only concern. If nobody
no,
has
sir,
any objection
what
to it,
is,
I'll be happy to do this, whatever
sir,
you are saying.
what is your suggestion, sir? Actually, we are very novice in this field, sir. If you
I would,
suggest me that whatever I am telling, this is are good for everybody, then it will be, sir. Actually, sir, you can take this class uh, 1 year ago also. I think so.
yes, I guess I did take it. Did I?
Actually, I went to your YouTube page, sir. I find that you have taken this session previously also.
Yes, I have taken them, but those are probably for the course Semiconductor Devices and Circuits. So that is a PG level course. This is a UG course. So that is one difference. So actually,
Okay.
the problems that I've showed you were at par with that course, and that is more tougher course than this course. So if you are comfortable with these problems that I showed in these live sessions, so you'll be very much fine with the problems that would be asked in the exam. That is my opinion. All depends upon the instructor. With regards to whether it would be fine to skip week 12, I'm not sure. I mean, that would depend upon the instructor, how much weightage he'll put to the last 3 weeks. Because if we focus on week 5 to week 8, because doing more than 4 weeks in one session would be a lot. I mean, I tried to do that last time. That took a lot of effort. So we won't be able to go beyond week 8, first thing. And then we'll be left with 3 more weeks, right? Week 9, no, we'll be left with 4 weeks, right? 9, 10, 11, 12. So, I mean, let's see what others say. If nobody has any objection, I'll revise week 5 to week 8. Meanwhile, let's start with this today's, okay?
Okay, sir. Okay.
Yeah, so I'll skip the guidelines now. So the prerequisites were the following topics that were covered in, not last week's, but uh, the 1 week before the last week, okay, because we skipped 1 week. So it's LEDs,
Week
the
11.
working principles, yeah, the radiative, non-radiative recombination, the various types of efficiencies, and yeah, blue light, Nobel Prize, visible LEDs, and chromaticity. Okay, so a brief recap. So a brief recap. What is the main idea, or I should say, the working principle of LED? Let me put it this way. LED, working principle. Okay. Would you like to add on this? What is the working principle of LED? I just need a one line.
Sir, it can convert light to electricity. Sorry,
What
it can
we are
convert reverse, sir. Opposite, sir. Electricity into
so
light.
I mean, I'll rephrase that. What it does is we are applying voltage, right? We are applying voltage. This is your PN junction. We are applying voltage to this. So in LED, we forward bias it, okay? And what happens when you forward bias the PN junction? We inject excess carriers, right? And we inject these carriers, and these excess carriers then have to recombine radiatively, right? I mean, recombination can be radiative or non-radiative, but we are interested in radiative recombination because that is what emits light. Uh, I mean, non-radiative. What is a non-radiative recombination? Examples:
Sir, heat, generation of heat, sir.
emission of
Phonon, sir. Phonon.
yeah, a recombination which is accompanied by an emission of and in which type of materials would that happen? Direct or indirect?
Sir, in case of sir indirect band gap, you can phonon recombination is there. For direct band gap, you can
Yeah,
photon recombination is there.
correct. I mean, even in indirect band gap, the thing is, the if this is not efficient, right? The recombination in indirect band gap, uh, it takes away the efficiency. Okay, because of this, what should I say? Uh, Due to the change in momentum, right? Because when it recombines from conduction band minima to valence band maxima in an indirect band gap, that is also accompanied by liberation of phonon, as you mentioned, right? Or I should say emission of phonon. So that compromises the efficiency, and as such, those materials are uh, not used for LEDs, right? Because the associated momentum change in the electron hole recombination affects the efficiency. Okay. So now, what are two primary non-radiative recombinations?
Yes, sir. What are the
Two types of primary recombinations that we discussed in the class. Let me first write the working principle.
sir SRH?
SRH and the other one?
Other one is auger and auger recombination, sir.
Yeah, Auger recombination. So we are injecting excess carriers, right? Forward biasing the junction, right? And which recombine, which recombine in radiative manner, okay? Which recombine radiatively from band to band, right? And I mean, light is emitted, right? This is what is key for an LED to work, right? When uh, those excess carriers recombine radiatively from band to band, emit photon, which we see as light. Okay. Now, and this light emission due to the current injection, there is a particular term for this, right? The light emission.
Is this photoluminescence?
It's electroluminescence, right? Because
Electroluminescence, right? Sorry,
yeah, light emission due to current injection. Okay? Now, with that, we'll start with today's first question. So the first question is, why can't the silicon be used to make efficient LEDs? What do you think would be justification, or should I say an
Due to
answer for this?
indirect band gap.
And
Due to
silicon is
indirect
an
band gap.
indirect. Silicon is
Indirect band
indirect
gap.
band gap, right? So what will right answer to this is silicon is indirect band gap. And what is the consequence of that? What happens if silicon is indirect band gap? Why does it not lead to efficient LEDs?
Basically, sir, when the conduction band minima and valence band maxima are not
Mhm,
in same K level,
mhm.
so we have to move means more path to generate generate the excess carrier.
Yeah.
We
So what
have
you
to
can
travel
say
more.
is your electron hole recombination, right? Your electron hole recombination has associated momentum change in indirect band, right?
Yes, sir. Yes, sir.
And that degrades your efficiency because part of your energy is, I mean, utilized in making this momentum change, right? So this one is done. So in other words, we can say the silicon cannot be used to make good LEDs, okay, or LEDs. So with that, let's move on to the next one. So the next question is, if Eg is your band gap, then energy of the photon emitted is, it is,
Greater than, sir.
yeah, it is greater than. And what is this energy precisely equal to? And before that, why is it greater than energy, Eg? Why not less than?
Sir, in the band gap there is no energy level is there,
Correct?
and to make the electron free,
Hmm?
we have to apply Eg greater than band gap.
Why greater than Eg? Why not Eg precisely?
Sir, if I apply greater than Eg, there is a loss is there, which is for recombination loss. Means that if I apply greater than Eg, then it can be also back to the Eg level after certain time. It's all
Okay,
non-ready recombination is there.
let me discuss it. So if this is your conduction band minima, and this is your valence band maximum, uh, where is, how are the electron and holes distributed? I mean,
Yes, sir.
as you as you pointed out, we won't have states here, right? In
Yes,
this
sir. Yes,
band
sir.
graph, VG.
Yes, sir.
So as such, we won't have free carriers here, right? So free carriers would
Yes,
be
sir.
here and here. Now I'm asking, what is the distribution of those carriers?
Sir, valence band is completely filled and conduction band is partly filled, partially filled.
So the distribution is somewhat, where is the peak concentration of electrons? It is situated above EC. Okay, it's something like this, not at EC. It's some energy level greater than EC. Okay, this is where peak concentration of electron occurs. Okay, this what I'm drawing is distribution of electrons. Similar thing is for holes, right? So for holes, we will have it somewhere here. So this is Ag, and then this and this. So, I mean, if we now say, how would they recombine? So we'll say your electron and for them to recombine, we need this much energy, which is which would be the energy of the photon emitted, right? H nu. And clearly it's greater than Eg, right? And
Can we explain one more, sir?
okay, so what I'm saying is in conduction band, you have distribution of electrons, right?
Yes, sir.
And in valence band, you have distribution of holes.
Yes, sir.
So have you seen lot of concentration of electrons in the conduction band? Can refer to Straightman Banerjee. I guess that book has it, or probably any other standard textbook. So the peak of electrons, it is situated above EC. Okay. Are you getting the point?
Okay, sir. Okay.
So
Yes, sir.
we
Yes, sir.
have very few
The actual
electrons here.
position of
Yeah, that is what I'm discussing. Yeah, the position. So it is situated, the peak of the distribution is above EC, right? And let's say it's some delta, and here it is also delta. Okay. Likewise, hole is situated below EV, below the maximum of the valence line. So in fact, then we went on to derive it in the lectures. Your H nu was Eg plus H bar square K square by 2. This is reduced effective mass. Okay. Reduced effective mass. And that is your 1 ME star plus 1 MH star. Okay. Yeah. What else? In fact, this delta here is H bar square K square by 2 ME star. Likewise, this here is H bar square K square by 2 MH star. Fine. And then when you add up them, right? Because for H nu, you need to add from this to this. This whole would be H nu, right? And when you do that, you will end up with this, where this is reduced effective mass, which is given by this. Okay, that's it for this question. So what is the answer of this? Take this one, right? It's greater than Eg. What about this? The emission spectra of LED. What determines that?
both, sir, it is the product function and density of states, sir.
Correct. It depends upon both the Fermi function as well as the density of states, because it actually depends upon the concentration, which is given by the product of these two. Right. So what I can write is I be proportional to Fermi function, the density of states. Right. So it's product of the two. So it depends upon the both. As this one was easy, I readily answered it. Yeah.
Sir, can you explain the last part of the question? The formula which I've derived, I think it will be beyond 4 weeks, sir. Please, no, not
This
this,
one.
sir. I know that. No, sir. Previous question, sir. Previous question.
This one. This one.
Yes, yes. This only the
Okay.
left part of
Okay.
right part of the.
Forget this one. Are you comfortable with this? That this distribution would be
Yes, yes,
slightly
yes,
above
yes, sir.
EC?
Yes, sir.
Then you can at
Yes,
least
sir.
still answer it and say that it's greater than EC, right?
No, no, sir.
Even
No,
if
sir.
you don't
You
think.
write the No, sir, sir, you write the formula which I have find in the sir lecture. Sir can discuss this. So if I
Probably
you
this is
just
from the lectures that were taught by YouTube. I mean, that were taught by instructor. I think sir has discussed this. I'll check it again, but I guess
no sir,
if
you
I'm not
just
wrong,
discuss this for if you discuss the formula directly, sir. What is the formula actually? If
this
possible, sir.
is the this is the actual formula, right? Okay, if I need to write it, uh, I'll write it. See, I told you h nu is equal to plus this plus this, right?
Yes, sir. Yes, sir.
Th- this part is h bar square k square by 2 me star. This is this part, right? This is h bar
Yes.
square k square by 2 mh star. So how
Okay.
will I write the sum of these three? It would be, let me first write Eg, right? Eg plus h bar square k square by 2 me star plus h bar square k square by 2
M
mh
M
star,
M H M sir.
right? And what I then do is I take h bar square k square by 2 common. H bar square k square by 2 can take common. We'll be left with 1 e star plus 1 by next star. Is this right?
Yes, sir.
And then I call this much as reduced effective mass, the reciprocal of that. So I'll write Eg plus h bar square k square by 2 and r square. Okay.
Okay. Okay.
This
Okay.
is what I wrote.
Sir, actually, you told that H mu means the amount of energy required to free the electron.
To emit the photon. Yeah, to emit the photon. In order for a photon to be emitted, you need your electron and hole pair to recombine, right? It needs to recombine, if we talk in terms of distribution, statistically over this, right? And this is clearly greater
Yes,
than
sir.
Eg.
So
That
the
is what
MR is the MR is identifies the recombination mass.
this is called reduced effective mass. This is
Oh,
just a
reduce effect mass.
notation.
Okay.
This is just a notation for this. I mean,
Okay. Okay.
write this if you get confused. I'm calling this as 1 by x something. In this is what it is. Or you can do one thing, you
Okay.
can write your MS, this reduced effective mass, MR star is star image star divided by right. It's either defined by
Okay.
this or this. Both are same. You take the reciprocal of this, you'll get okay. This is
Okay.
done, right?
Thank you,
So
sir.
now, okay, no issue. Now the peak emission wavelength of an LED, right? So
Sir, Eg plus KT by 2, sir.
it's EG plus K by KT by 2, correct. So this, let me still draw this and let's have a short discussion. So this is your I versus E, right? And it somewhat looks like this. Starts, it starts at what? What is this?
EG, sir.
This
EG.
is, yeah, correct. This is EG. And then as you mentioned it, the peak emission occurs, the peak emission wavelength, it occurs corresponding to energy that is Eg plus KT by 2. So this is part, I mean, this is situated KT by 2 right to this, right to the band. So now, uh, so as you say, the correct option is this, and this occurs at E is equal to Eg plus KT by 2, right? And as you can see from this plot, your emission, it doesn't happen at one wavelength, right? Does it?
Yes, sir.
It does not, right? I mean, corresponding to each energy, you'll have a corresponding wavelength. right? How is energy and wavelength related? E is hc by lambda, right? So for each E, you'll have corresponding lambda. So for this, you'll have hc by, let's say, lambda g. For this, you'll have hc by, wait, what would be the wavelength corresponding to this? The energy E, Eg, sorry. Use this
Sir,
form.
EG, here EG, why uh, it
Hc by
why
Eg.
does
I
it
guess you're Hc by
why
Eg.
does EG F, FC by EG, sir?
Right?
Hello, sir.
Yeah.
Why EG, sir, start from uh, why does not it start from zero, sir?
Okay, you're
I think
saying why doesn't it start from zero, right?
yes, sir.
Because
Yes, sir.
see, in order for it to start zero, if it would start at an energy that is less than Eg, then you are saying that your recombination happens across a delta E that is less than Eg, which is not the case, right? I mean, as we discussed, the distribution is something like this. I mean, at this EC, the concentration of electrons is zero, and then it quickly uh, gets maximized and then falls over. Similar thing happens here, right? So the concentration of electrons here at this edge is zero. Here, the concentration of holes is zero. So at Eg, it would be zero. And then beyond Eg, you'll have a finite emission, right? But less than Eg, you won't have any states here. Do you have any states here? You don't, right? What determines your electron and hole would recombine? Allowed states, right? You are not having any allowed state here. So there is no way your emission would occur at an energy less than Eg. Is this clear? Is this
Sir,
clear?
kindly repeat, sir. Kindly repeat, sir.
Okay, I'll repeat it again. Did you get this point? What is this?
The emission of photon, sir.
No, no, no. This is distribution of electrons. Okay. Let's suppose this is N, or say, let's suppose this is E, right? Now, or N, whatever. Thing is, at EC, this drops to zero, right? This is zero level. Okay. Here it drops to zero at EC, and then it would remain at zero. Want it?
Yes, sir.
Why? Because you don't have any allowed state here. But as you increase your energy greater than EC, it reaches a maximum, right, that is situated slightly above EC, slightly above the valence band minimum. Right? This is your valence band minimum, and the peak occurs here. So what you conclude from here is, and similar thing is for holes, right? See, at your valence band maxima, the concentration of holes is zero, and it maximizes and then drops away. In this band gap or forbidden gap, you don't have any concentration of holes, right? Because you don't have any allowed state at all. So what we conclude from here is that now, when will this emission happen? When will this emission happen? Emission of photon. Try to answer it. Doesn't matter
When
if it's
the
wrong. When?
when the energy greater than Eg.
Yeah. And for that, I mean, the point was when your electron and hole would recombine. And if you don't have any electron and hole here, so the values of energies that are less than E, G, for corresponding to those, your emission would be 0. Does this make sense now? Does it?
Yes, sir.
Okay. And once you're this EG, at EG it's 0. But even if you move slightly greater than EG, you'll have a finite emission. Why? Because it becomes non-zero. It becomes non-zero. This is for electrons. This is for holes. I hope I made it clear. If you still have doubt, you can skip. The question was from Sanjeev. So, Sanjeev, are you convinced?
Yes, sir.
Okay, thank you. So now it's clear, right? Why it's 0 here and then it starts gaining. So what do you think is happens here? Eg plus kT by 2. Here we'll have peak electron and peak hole, right? The peak of the distributions, right?
Sir, maximum intensity.
Yeah, the maximum intensity occurs here. So now what I was coming to is, thing is corresponding to Eg, what would be your wavelength? See, the point is now you won't be having emission at only one wavelength, but it's rather distributed over a range of wavelengths, right? For each energy, E will have a corresponding wavelength. E and lambda are related by this formula, right? So what I'm saying is, for this Eg, what is the corresponding wavelength in terms of Eg?
The small cell.
Small, but I need the value. It would be Hc by Eg, right?
Yes, sir,
Take
yes.
lambda here, E here. It would be Hc by Eg. Similarly, you can compute the wavelength corresponding to this energy, right? It would be Hc whole divided by Eg plus kT by 2. Correct?
Yes.
Fine. Then what? Then yeah, your peak emission wavelength of an LED occurs at E is equal to Eg plus kT by 2. Your emission doesn't happen at one wavelength. It happens over a range of wavelengths. Then we have a quantity called full width half maximum. What is this quantity? This is your peak emission, right? We take half of that. Half of that would correspond to somewhere around here, right? See, if it's I naught, this would be I naught by 2. Is it fine now?
Yes, sir.
Right, I'm taking half. What I'll do is I'll see this distribution and I'll record this peak and then I'll divide by 2, right? And now I'll obtain the two values of the wavelengths corresponding to this, because if you see, this intersects this at 2 points, right? This and this, right? This particular range, which is equal to this range, this delta lambda is full width half maximum. Okay. So we are done with full width half maximum. It's delta lambda. Okay. It is a range of the wavelengths over which the peak spectra is happening. Okay, because if you see, the peak of this spectra happens across this range. Okay, the significant portion. Is it?
Yes,
Yes, sir,
sir.
it is clear, sir.
Okay. Because here and here, we can neglect that, right? This is the peak of the spectra. Now, what else? Okay, now this wavelength spread delta lambda, right? In this. Is it constant for all lambda? does it increase with lambda? Does it decrease with lambda? Or is it independent of temperature?
Sir, increase and decrease both, sir.
Increase and decrease both. How? How would it increase as well as decrease? It has to be
Sir,
either of
you
the
say
two,
that
right?
no, sir. You say that wavelength spread.
Yeah.
Your previous drawing is say that for a below range for EG by EG plus KT by 2 below range, it is increasing.
I guess you are getting confused. See, by delta lambda, I mean this. This is your delta lambda, right? This range, right? This particular quantity, right? Right. This is your delta lambda.
Okay, okay. Then it is increasing, sir.
Right? It increases. And what is the formula that governs it? In fact, the course instructor showed the formula as well. Right. So the formula is following: your delta lambda is approximately your 1.8 kT by hc times lambda square. So it goes square of lambda. Okay, I mean, accordingly, question could have been asked, right? Say, suppose the ratio of the delta lambdas. In that case, you have to take the ratio of wavelengths given the temperature is constant. Only then you can do that. If temperature is not constant, you are given two separate temperatures, then you need to, I mean, then you'll have T1 lambda 1 square by T2 by 2 square. Right? Delta lambda 1, delta lambda 2. Is this fine? So this is wrong because it does depend upon temperature.
Yes, sir.
Okay. I mean, you can come up with more variants of this problem, right? Given this formula. So what about this? Suppose you have a red LED and you have a blue LED. This full width half maximum delta lambda, right? For which LED this would be larger? I'm giving you two, right? I'm giving you red.
Red, sir. Red, sir.
I'm giving you blue. But why?
Because, sir,
Why?
the delta lambda it depend upon, sir, lambda.
Correct. And
If red, in case of red, the lambda will be around, I think, 300.
I guess it's greater than 300. I guess it's close to 700 nanometer. But whatever, I mean,
And
that is not the point. The thing is, the wavelength of red LED is greater compared to the wavelength of
yes, sir, yes.
the blue LED. So that is why the
green, sir, green, I think 565, na?
see, if I'm not wrong, the visible range is from around 300 to 700 nanometer. We can check it. I'm not sure, but
No, sir,
it has to be
I say
around this.
that green
That's
is
why green is what? We can check. Wait,
565, 565, sir, 565.
yeah, it could be 5 because it falls between the two, right? If it's
Okay,
300 or 400, I'm not sure for this. 300 to 400 nanometer. And this would be around 700 nanometer. Just check it. So green can be in between. So your delta lambda would be in between. When you you can have a different question in which your three LEDs would have been given, right? And then you would have been said,
okay.
write the order of this delta lambdas. You can accordingly write it. The thing is, you need to focus on wavelength, right? That was the essence of this question. So now the last one is, what is the relationship between the recombination rate and
Inverse, sir, inverse.
what is inversely proportional? For
R equal
example,
to, sir,
1 by tau,
R equal 1 by tau, yes.
right? Suppose I tell you what is the recombination rate for what is the radiative recombination rate? You'll say 1 by tau rad. What is the radiative lifetime? We'll take inverse of that. That would be the radiative recombination rate. Similarly for non-radiative case. Is this clear?
Yes, sir.
Okay. So that finishes this week 11. I mean, whatever problems I have. I mean, I only touched few things.
Sir, would you please repeat the question?
Last question.
Easy by. Oh, sorry, easy. Why easy starts from apart from zero?
Okay, I guess you still were not convinced. You're saying why it starts from 0, right?
Why does not start from zero?
Okay, why does it not start from 0? I try to answer this. Let me take 3 cases. That would probably answer your question. Let me take this case. Let me insert a different page. How do I add a page? Okay. This is what I need to do. We'll take case 1. In this case, first of all, what is this axis, Sanjeev?
Sir, easy.
This is not EG, this is E. Okay.
Easy.
E, precisely E. Neither EC nor EV. It's E, energy.
Okay, sir.
Okay. Now, this is EC, this is EV. Let's say this does not start from EG, and instead, as you said, why does it not start from here? Right? Why does it not start from here? Something like this. Right? For this
Sir.
to
Yes,
be
sir.
possible, you need this emission, right? You need emission probability at EG less than 0. Sorry, E less than EG, right? Case. If at any point of time you don't understand, interrupt me and ask me. Okay, I'll stop and try to explain it better. So now, I occurs at E less than EG. Right. For this to happen, what you need is, where should electron be present? See, in order for
between sir, EG, sir.
Between EG, you are saying that electron should be here, right? Somewhere around here.
Yes, sir.
Where should hole be?
What, sir?
See, for photon to emit or light to emit, you need electron and hole, right? And they have to recombine. As you said, I put.
Yes, sir. Recombine.
Yeah.
Recombine, sir.
Where is hole present in your case? Where should I keep hole? Should I keep it here?
Near to sir. Near to EV, sir.
Okay, near to EV, but near to EV has 2 ends, this and this. Where should I keep it? Above or below?
Upper, sir. Upper.
Above? Okay. I'll keep hole here. Okay, this is what you are saying, right? The problem with this is,
yes, sir,
you cannot have concentration of electrons in this forbidden gap. Why? What determines the concentration of carriers? It is the product of this Fermi function times G of E, density of states. What is zero in the band gap or in the forbidden gap? This. This is zero. You don't have any allowed state, right? Because that is the definition of forbidden gap. You don't have any allowed state in the forbidden gap, right? In fact, the name itself signifies that forbidden energy gap. What is forbidden? Energy states are forbidden here. You don't have any states here. If you don't have any states here, so this is zero. If this is zero, the product with this would be zero. So in other words, electron cannot be here. Hole cannot be here. Okay, is this clear?
Yes, sir.
So where should now electron be? Let's correct it. Okay, first you answered that electron should be here, hole was here, but I somehow came up with a justification to counter your argument. Now, where should I keep this electron? Let me move this. Where should I move it?
Sir, EC, on EC.
On EC. At ECH,
Yes, sir.
where should I move hole? Since it cannot
On EV.
be on EV. But point is, even if you keep it on edge, still this product is zero, right? Only when it is slightly greater than EG, okay, it has to be slightly greater than this. This has to be slightly set away from EV. So that is the reason at EG it's zero. And beyond this,
Yes,
what
sir.
happens?
Yes,
See,
sir. I got it.
if you take EG, if you take this electron more and more up, this would increase. The thing is, the distribution peaks out somewhere here. The distribution peaks out somewhere here. That is why you have peak here. As you go from EG to the peak, as you take this, you'll have more this, right? Because there are more number of electrons and more number of holes situated corresponding to, I mean, here and here. Is this clear now? I mean, I tried my best.
Yes, sir. I understand. But,
Okay.
sir, how much upper
Yeah.
and how much upper electron and hole would be there?
Okay. It's around half of kT in terms of energy. This is precisely this. I mean, this peak occurs at a distance, at an energy that is greater than h bar square k square by 2 me star then. Is this clear now?
Sir, this is Schrodinger independent of Schrodinger equation.
Why would it be
Time independent
independent?
Schrodinger. Time
Yeah,
independent
that
Schrodinger
is
equation.
that. Yeah, I mean, you can use that. The point is, I need the solutions, right? The allowed energy values you get from the Schrodinger equation. So yeah, from time independent Schrodinger equation. Does this answer your question? I mean, you can get these from
Yes, sir.
textbook also. If you
Got
are
it, sir.
confused
Got
with
it.
this, yeah. Okay. So that was, I will write this as hypothetical case since I did not need more cases. This is your hypothetical case. So we justified this cannot be. So it has to start from here. Right? Or in other words, it will be zero here. So that, I guess, finishes this session. What we can do is, does anyone have any doubt from today's session or uh, from any of the uh, first 4 week sessions? Any doubt?
Hello, sir.
Yeah.
Sir, I have a doubt in questions like what is the width, depletion width in Schottky barrier and an ohmic barrier? How they are equal?
How the depletion widths are equal in Schottky barrier and ohmic barrier.
No, not in Schottky barrier. How the depletion width is equal in forward as well as reverse bias? This is the question.
Can you type it in the chat? Just type it in the chat. Want to see the question?
Sir, it was from assignment question.
Okay, is this assignment question?
Yes, sir.
Then I can check it online as well. Just a second. So which week is this? Week 5, probably, right?
Sir, topic is Schottky junction.
Yeah, and that was in week 5. Where is the question? Can you tell me the question number? Because I'm not able to find it.
Please give me 5 seconds.
Yeah, please. Meanwhile, anyone else who has a question?
Sir, up to 2 weeks, I can revise. I have no questions, sir. Everything, whatever you can discuss, it's clear, sir. And today, LED session will be clear, sir.
Okay. I mean, I did not cover the entire portion in LEDs. Do try to do more problems on this. I mean, we had very few problems on LED. Should we touch week 5 today? If you guys,
Yes,
free.
sir. Yes, sir. If time is there, sir.
Yeah, if time permits, why not try week 5? So, Yash, you can look for a question. Meanwhile, we'll start with this week 5. Okay. So this was week 5. In fact,
Yes, I
Yash
find
question
the
was.
question. So the
Did
question
you
number
find it?
11. Yes, sir.
This question
Assignment
11.
5, question number 11.
So this is okay. This is Schottky barrier height in a metal semiconductor junction. It increases. It reduces during forward bias and it increases during reverse bias. I guess we discussed that, right? See, what you have that question open, right? What happens in reverse bias? It increases. Correct?
Sir, 1 minute, sir. 1 minute.
Yeah.
You just
Sir, the answer given is false.
The answer is false. Yeah, I mean, answer has to be false because it's probably the. Just a second. See, our Schottky barrier height is not changing, right? What is the Schottky barrier height here? This, right?
Yes, sir.
And when you reverse biases, although the bands are bent, but still this point, this remains there, right? So this delta would still be this. You understand it?
time, sir. One more time, sir, please.
Just a second.
Sir, so basically, what happens that during forward as well as in reverse bias, the Schottky barrier height, that is Q5B, does not changes at all in both processes, forward as well as reverse.
Yes, I mean, I'll still double check this, but I don't think it will change here. Because I don't know if you are- I'm renaming the formula. And it was yeah. In my opinion, yes, it won't change. But still, I'll double check this one. What do you guys think?
We have also got the negative marks, sir. We have also tried true in that case.
Okay, you guys have answered it true. Is it?
Yes, sir. I've also answered it true, but the correct is false. That is given answer is false.
Okay, okay. Just give me a second. Were you provided answer keys or something? I mean, the solutions? No.
This
I mean,
particular subject we have not. This
I mean, I
particular
understood.
subject we have.
See, the reason I'm saying this statement is not true is because what determines your Schottky barrier height? The Schottky barrier height is determined by the difference between your metal work function, right? Metal work function and the affinity, right? Electron affinity. And if you apply bias, this particular difference remains unchanged, right? Because both of them are material constants, right? Material property, and that doesn't change with bias. So whether you apply a forward bias or a reverse bias, this difference won't change. This particular quantity will remain. So I guess this is it. I mean, I'm sure. So this won't change. So even if the order would have been reversed, say it would have been uh, increases, sorry, reduces. Uh, yeah, that is the way. Increases, reduces during forward and reverse. Still, the answer would have been false because the thing is, Schottky barrier height doesn't depend upon the bias. Is
Okay,
it
sir.
fine?
Okay, sir.
Now, what else we were discussing?
Sir, which is the answer, sir?
Yeah, which is the answer? I mean, we answered
Yes,
it
sir.
false. Okay, you mean the question? It is from your which assignment? Your week 5 assignment, and it is problem number 11. Yeah, the problem number 11 for week 11 assignment. That is what we were discussing. I mean, it has nothing to do with this.
How do we,
How do?
sir, answer will be, sir?
Answer will be false because uh, the Schottky barrier height is determined by the difference of your uh, material constants, right? I mean, for example, this metal work function and the electron affinity in the semiconductor, both of them are material constants, and that they don't change with bias. See, if you apply bias, you can shift this. This will also shift in a way that this particular energy range, or say this affinity, remains unchanged. Affinity has nothing to do with bias. That is simply the answer of this. That is why it's false. Fine.
Yes, sir.
Okay, now we were saying that we'll revise this. So this was good. I mean, this was 2 in 1. I mean, I thought of revising week 5, and incidentally, the question that Yash asked was from week 5 itself. So now let's see what were the questions that we discussed now. In a certain Schottky contact, a negative bias is applied. Right? You guys tell me, do you have any questions from this? Because you would have already, I already went through them, right? So how I approached this question was I first made an equilibrium band diagram. Okay. And then I considered the case of equilibrium and the reverse bias case. These two cases are different, right? And See, when you apply the reverse bias, bands will bend in this direction, correct? Because a positive here would bring them down. And when they come down, what would happen? Oh, sorry. This curvature, I mean, whatever you say, the slope, this would become more sharper, right? Correspondingly, your this phi would be more slopier. If phi is more slopier, then your electric field is simply the slope of this. So you'll have more magnitude of electric field. And we all know when you apply reverse bias, your depletion width increases. That is the reason this is the correct combination. Your peak electric field increases and your depletion width increases. Is it fine?
Yes, sir.
Then we have next question. Okay, this was numerical one. I'll leave this. I mean, it was nothing but plug and play, right? This was simply the difference of these two, right? And then you had to determine QF, this Q5F, you can determine using this formula, right? And then phi BI was your bulk potential. So this is self-explanatory. I'll leave this. Then you had this, consider a metal work junction found in the previous question. Instead of N-type doping, now consider the P-type doping. What will be the Schottky barrier height? So when you have P-type doping, your this would be the equilibrium band diagram. Okay. And this would be our Schottky barrier height. This would be our building potential. And this would be our Q5 bulk potential. Now, first we obtain Q5, right, using the doping values, right? And once you obtain that, is it Q5B? Just a second. Q5B. Okay, your Q5B is 0.67, right? And when you subtract this Q5F from this, you get the built-in potential, right? Because Q5B minus Q5F is Q5BI. Then we have next one. In this, you had to obtain this electric field at the metal semiconductor interface and the depletion layer width, right? This is your depletion layer width in micrometer opacity. This is your peak electric field at the interface. These are numerical based. I mean, in the previous question, we obtained XD. Now you substitute XD here, put in the value of epsilon s, you obtain CG as this. So then you have capacitance C of a Schottky barrier diode that is given by this relation. Okay, giving an empirical, you are given an empirical relation, right? 1 by C square is A minus BV, right? Now what you do is you write C is equal to epsilon S by XD times A. Right? C is equal to epsilon S whole divided by what is XD? XD is this. Square root of 2 epsilon S pi Vi plus VR whole divided by QND. Right? This is your XD. Once you obtain C, this is your C, right? And you take inverse and take square of them, obtain this. And then you need to split them, end up with this. Right? Here A is what? A is this, and B is this. You have A and B. And then from here, this is A, right? Where A is equal to this. From this, you can obtain 5EI in terms of A, right? Are we missing anything? Correct. You can obtain 5EI in terms of A, and likewise, you can obtain ND in terms of what? B. Are you able to follow what I'm saying?
Yes, sir. Yes, sir.
Okay.
You just put there is multiplication is there. So
Yeah, I
it's
mean,
5bi
this
by
is just,
a square.
yeah, correct.
Just put the value.
So you got it. So now, then you have this, you know, this relation, right? Electric field at an at a distance x, right? That is q and d by epsilon s x minus xd, where xd is this square root of 2 epsilon s pi bi minus v. This is known. So wait, your v is minus 5 volt. Okay. Then obtain this, right? What you need to do is simply plug x equal to 1 here. What is this? xd. Where is xd? Yes. And it was fermionic emission that depends upon the shape of the band bending inside the semiconductor near the junction. Yeah, that's it. I mean, the rest of the problems, you guys have a look and then you can let me know if you have any doubt. Okay. In the next session, I'll see if I'll touch week 12 content or I'll have 3 or 4 revise week sessions. If that depends upon the comment, right? I mean, I'll post the video and if I get the comment, we'll accordingly take that decision. Okay. Or maybe even you
Thank you,
guys
sir.
can even you guys can post your suggestion in the comment. You guys can say that uh, we would like to have a revise session in tomorrow's extra session. By the way, extra session is tomorrow, okay? Tomorrow 3. So that others would also know if they don't watch this video completely, they'll still know that what's going on, that we are planning a revise session. That's it from my side. I'll be ending this video now. Okay, I'll stop the recording.
Thank you, sir.
Thank you.